All right, so we are now about halfway through geothermal, and I did email the publisher to get the second half of the figures, but I did hear back, but my access was taking a little bit of time to renew, so we'll finish up the chapter, and I'll just refer to the figures as we go. So I am now on page 441, and it's box 9946. So the EGS, Enhanced Geothermal Site at Sault-Sous-Forte. This is in France. And I'm just going to read a little bit from the book here. It says the Sault site, like Fenton Hill, benefits from the blanketing effect of 1,000 meters of sedimentary rock above the crystalline basement. The geothermal gradients, which we talked about last time, we did a little bit of Darcy's Law. It was kind of fun. We ran some vector notation, we ran some tensor notation, talked about the difference between pressure being either a scalar and stress being a tensor. We also looked at the fact that the heat equation looks a heck of a lot like Darcy's Law. So just how you have a permeability constant for Darcy's Law, fluids flowing through rocks, you also have a thermal coefficient or tensor on how heat moves through things. So they're talking about two different types of rocks and different permeabilities. So geothermal gradients, we're looking at 0.06 to 0.1 degrees Celsius per meter, and this falls to about half of that in the basement beneath. Okay, so Italy and Switzerland worked together on the site, eventually drilling 4 deep boreholes greater than 3,600 meters, and they were hitting 170 Celsius. Nice and hot down there. Several shallow boreholes that used for microseismic monitoring systems. And they're actually talking a little bit about geophysics there. It says where the east-west tensional forces have stretched the crust and caused the granite basement to subside. The basement is heavily fractured and even supports a small amount of natural fluid flow. So in the figure, and sorry I can't really show it to you here, but the earth is literally stretched and cracked apart. And this field it's big. I mean, the scale bar down there, 500 meters. I mean, it's a couple miles wide. And when you're drilling, drilling 3,800 meters, that's, what is that in miles? 3,800 meters, 1 point, so that's a little over 2 kilometers. It's about a mile. So they're drilling about a mile down. Is that right? No, I'm sorry, 2 miles. Yeah, it's 1,608 meters per mile. So yeah, they're 2 miles beneath the surface, and all the way down to 5,000. So they're actually 3 miles down, and that's what we're seeing in the right half of that figure. Each one of the geothermal boreholes has been named, and they're all the way down at 200 degrees Celsius. So then they said, with careful control of the pressure and density of the stimulation fluid, the stimulation zone can be persuaded to develop laterally so that it can be accessed with the conventional arrangement of 2 or more boreholes. So this is a little bit like your horizontal drilling, right? And I think I told you when they were drilling the new utility lines in my yard, it was wild. So at the end of this drill, the drill head itself was sort of at an angle. It was sort of always drilling at 45s, and there was a little shoe on the bottom that was always forcing the drill to drill off center, and the shafts on these things are flexible enough that even though it's bent, it's still spinning, and then you can spinning inside another shaft, you can control exactly the angle and really basically drill whichever direction you want. Yeah. Okay, and I think that turn the lights on here, 'cause it's just dark enough at 4:30.
Oh, hey.
Is that okay? You want yours on back there? And there's also, I don't know if you need something. Okay. Okay. So figure 19.4, figure 19.4, 914, yeah, sorry, thank you, is, I'll get there eventually, just showing the control field. So each one of the boreholes has its own set of pipes. You can see off to the right, there's a little bit of steam, so the temperature and pressure is being controlled, and they're looking at 1.5 megawatts equivalent coming out of here. So at 200 Celsius, obviously, you can boil water and make electricity. So the turbo generator first generated in 2008, and so there you go, 1.5 megawatts of carbon-free electricity coming out of the ground. The only byproduct right there is a little bit of steam in the atmosphere, no giant ash pile, what have you. Okay. Next down here says, perhaps the most surprising entrant in the geothermal stakes over the past decade has been Australia. Previously it had been assumed that the age of the Australian crust meant that accessible temperatures would be too low to be usable. Now by that, I assume that it's so old that it's cold. That's just what I'm going to go with on that one. But that changed in 2000. The federal government said, let's go. In 2011, 56 companies held exploration licenses in 418 areas, and they're there. You can see the licenses are numerous, a lot in Tasmania, and the wells themselves mainly focus, gosh, a lot of wells in Tasmania, but several in South Australia near Adelaide, as well as Melbourne. $671 million spent by 2011. And they say, at least by 2015, they're looking at $3 billion. And they also say a lot of it's private too. And not unlike, I think, what we're seeing now with the climate change studies, where it seems like there's going to be a lot of private money flowing into renewable energy technology. Okay, the most advanced EGS project being developed is by Geodynamics in the Cooper Basin. 5 wells. I like how they called one of them Habanero for the drilling. Okay. All right, now there are environmental implications. We talked a little bit about going through water tables. Obviously, a forest could be threatened. They talked about rivers being polluted. So just like, geothermal energy is not unlike mining. I mean, you're poking a hole in the ground. Gases can also be released. And these are mentioned as non-condensable gases, so lighter than air gases: CO2, hydrogen sulfide, sulfur dioxide, hydrogen. It also says that anytime you're boring a hole this deep through zones, I just did mention that these rocks are under tension, and you all know what happens if you got a piece of paper under tension. You poke it, it's more likely to fracture. So that's Also, that's what they're talking about with induced seismicity. And even the case of fluid injection, it says that you're lubricating fractures, causing them, to break apart even more prematurely. Also mentions that low enthalpy systems, we talked about what enthalpy was last time, it's joules per kilogram, it's how much thermal energy there is per given mass. In low enthalpy systems, the reinjection maintains the pressure, and seismicity is not typically as big a deal. Okay. Take a look at figure 619. If you remember a couple lectures ago, I talked about normal forces, and what they're showing there in 619 is that they've got sort of small normal forces in the top and bottom with those small red arrows, and then they've got much larger lateral forces, normal lateral forces with the larger arrow, and then of course what they're showing it that the result is that the material is subject to sliding. So right in that one little picture, you can almost see your stress tensor at work. And this whole enhanced seismic activity is not a hypothetical thing. It actually says that there have been resulting seismic activity in the U.S. That's mentioned there in box 9.7. Yeah, and it does say in Basel, Switzerland, and this is the rig that's shown in figure 917. It says it was forced to close when a hydraulic stimulation operation of the first borehole did trigger several small events. So 3.4. Now it's interesting. I'm not sure why you would then just go ahead and close it. In my mind, there was probably some stress there already. You relieve the stress. The rock reset. I mean, the Earth's going to continue to move. I shouldn't say nothing. You should never want to say nothing. There's relatively little with our current technology that humans can do to affect to negatively affect seismic activity on Earth. The Earth will continue to cool. It will continue to quake. I'm sure there are things we can do to advance that, to make it happen more quickly. But on the other hand, I would look at that and say, well, there was stress there already. I caused this mini earthquake, or maybe not so many, 3.4 magnitude. Maybe it resettled to something that's going to be stable for the next 100 years. So, and I've gone to talks where there are some engineers, geophysicists trying to predict earthquakes, and it's a risky business, but I kind of look at that system and say, well, maybe it's time to figure out a way to run it unmanned, right? So do you really need someone there to pull the triggers and switches? Don't we have remote control apps for all that now? So rig it out. If it okay, so maybe it becomes a little more expensive, but you're using it as a test bed for new remote control technologies, and if it falls into the ground, too bad. At least no one was hurt because you've got your sensors in place. Anyway, it's a tough call because you can see there's a lot of investment and a lot of infrastructure there. Okay. Now, we've also mentioned that globally geothermal is very significant. It was like 130,000 years or something like that if we were to use all the geothermal resource available under the continental U.S. It also says, and as we saw just recently with Sean's summary 4, it's available consistently, unlike the wind. The only thing that changes, at least if you have a low enthalpy system, is the demand depending on the season or the time of day. Unfortunately, a lot of times this is just driven by market forces. The price of oil tends to drive geothermal prices up or down. And now table 9.5, we're looking at a couple of Italian plants, one at 60 megawatts, another one at 20, another one in Japan in the late 90s. And these aren't small, they're not huge, but 60, 20, 50 megawatts. The maximum load is close to that in each case. The capacity factors are fantastic. You know, they're running at 96%, 95%, 85%, and the availability is even better, 99, 96, 92. And the availability is just when it goes down for maintenance or what have you. I'm surprised the Italians are ahead of the Japanese on that. You kind of think it'd be the other way around. If you've ever ridden on the Italian train system, it's pretty unreliable. I've never ridden on the Japanese, but I would think they're be a little more timely. Anyway.
Right?
Yeah. Yeah.
Hey, when you go from Germany to Italy, it's like, whoa.
But and like, how does the whole thing even stay synchronized? Yeah. Okay. Now I'm looking at figure 918, and see, these are new build generation costs, and they've got the systems rated in dollars per megawatt hour. And I guess that's over the long run. So it's in hundreds of dollars per megawatt hour. So $100 per megawatt hour would be the same as a dime for a kilowatt hour. So right there in the middle of the figure is the number 100. That would be a dime per kilowatt hour. Now these are the costs, and I think this is the what it costs the company. So it's a little more expensive than what we see what we see stateside. Now let's just compare them. And what's pretty impressive, and I guess this is why this is such a great technology down under. Remember, this is New Zealand. The geothermal is way down there. 6 cents, maybe up to a dime per megawatt hour. I'm trying to see if there are any counterexamples, but in general, the bigger systems. This is a little bit counterintuitive to me to say that the bigger systems actually cost more per megawatt hour. I'm not sure if that's because there's more to break, it takes more people to operate. Typically, I would look at this and think, gosh, it'd be the other way around. Anyway, but we're looking at New Zealand, and just because of their relatively high enthalpy areas, they say Philippines 10% in New Zealand. The total amount of geothermal electricity, some 67 terawatt hours, accounted for only one third of percent of global electricity consumption. That's actually the next figure. So Iceland's at the top, El Salvador's there, Kenya, the Philippines. We just looked at New Zealand. 10% is nothing to sneeze at. United States, we're only at a 0.5%. I'm sure we're bigger by now. But if you look at the rest of the world on a global average, only 1/3% of electricity comes from geothermal. Okay. Now, let me just read this little bit on looking to the economic futures. It says, the economics of future EGS developments are speculative at the time of writing and will remain so until the technology is fully demonstrated. Best estimates derived from recent progress. and reductions in drilling costs, and for sites with a temperature gradient of 35 Celsius per kilometer, is that we might get down to 12 to 20 euro, or 0.12 to 0.2 euros. So, approximately a dime to 20 cents, which is competitive with all other energies. They've done a little bit of cost modeling, and I think we're actually ahead of the book on a little bit there, because we from what Sean's done in his summary 4, we can very easily come up with a payback period. If you put in sort of your dollars per watt up front, your dollars per kilowatt hour over time, that will give you your payback period. Okay, next one here, we're looking at geothermal potential in the UK. So we've already looked at Australia, now let's take a look at the UK. And it's sort of separated by zones, and this is more or less a heat flow map. And if you remember back, we were looking at that. We took a lot of time and derived that 60 milliwatts per square meter, if you remember, and I said that's a global average. But if you look on this map, there are some places that are as high as 90 milliwatts per square meter, and some places that are as low as 40. So there are these Mesozoic basins, as well as the radiothermal granite batholiths. So it sounds like there are places where you actually have a little bit of radiation causing the heat. And I don't know if you've listened to much of this in the news, but one concern out of the fracking is once you're getting that deep with some of this stuff, you actually are starting to get into radioactive material. Not intentionally, but everything's down there, and once in a while you hit some radioactivity and bring that up to the surface, and now you have workers that need to wear Geiger counters. Same thing is true if you're digging deep for geothermal.
Is that just for the systems that actually have emissions? Because isn't there like dry steam or ones that like just cycle without emitting?
Yeah. Well, because in all these systems, you're always going to involve some kind of mass transport. Whether it's right. Otherwise, none of them are just based on pure radiation. I mean, in every case, you're dealing with some kind of conduction. So, a fluid, whether it's a liquid fluid or a gaseous fluid, is going to be moving, and just trying to think from a radiation standpoint. I guess if you have a closed loop, and this is typically the same way a nuclear reactor would work. You've got one fluid that's exposed to the radioactivity, another fluid that's separate and contained, so that would reduce the amount of radiation. But something to consider. Table 9.7 just gives a list of the completion dates of several UK wells, the depths. So again, we're deep, between 1 and 2 miles down. Temperatures close to boiling. They're looking at the aquifer, so they're certainly well into the aquifer, and the aquifer itself being cooler, close to 55. Close to 55 degrees Celsius, actually. It's kind of relatively warm at that depth. Now, right here, this is fairly substantial, because if you look at table 9.8, the numbers that we're seeing are actually in exajoules. So this is the potential UK geothermal energy resources at different temperatures. So if you're 40 to 60 C, we're looking at 26.2 joules. If you're less than 60 C, actually no, this is oh, I see. So what they're saying in the 40 to 60 C resources, they're actually using pumps, whereas in the hotter, they wouldn't actually use heat pumps. So the Q dot, the heat flow is actually less. Again, at those temperatures, you're looking at heat rather than electricity. Okay. Next little figure, 921, and so you might look at this and say, well, gosh, there was exponential growth in the number of heat pumps installed per year, several thousand per year, peaked right around 2008, and now we're down to 2010. Now, exactly why we did not see that increase? Variety of reasons. It could be that just there are no more permits allowed. I don't know if the UK had similar financial issues, there just wasn't money available to invest in energy then, but for whatever reason, it sort of went back down in 2010. Okay, we've just got a couple more little figures here, and I think we're done with the chapter. So, figure 922, engineered geothermal systems. Now we're looking just at southwest England, and they've done some kind of thermal gradient mapping, and this is at 6 kilometers, so almost 3 miles down, the same depths we've been looking at up to now. Hitting some pretty high temperatures, so 240, 230 degrees Celsius. That's enough to make electricity. So they're talking about a suggestion of 300 to 500 megawatts of electricity. Compared to coal strip's running at 2 gigawatts, so it's only a quarter of that. But on the other hand, it's in a relatively small place, and I think that the transmission losses are not going to be quite as great. And I also know that a lot of the appliances in Europe are a little more efficient than what we tend to have here. Okay. Yeah. So this is something that the UK is definitely thinking about. Tens all the way up to hundreds of megawatts. Okay, and then the last little bit, it's legal and regulatory issues. So they said they can be a technical novelty to a commercial reality, and not cheap to put in, of course. And, I like this next one. It says, central to this question is resource ownership. So not only must developers or their banks be confident they have a right to the resource that they will be extracting, but there also must be a provision to protect the developer's rights so that the developer can continue to develop. Also, protecting the rights of third parties, neighboring developers or property owners if you end up drilling into their property and messing with their aquifer, that could be a big deal. Just as every country has its own legal code, every country with a geothermal industry has defined these rights and responsibilities according to its own background. And I think this makes sense. It says the ownership is reserved for the national or regional authority, and then the national or regional authority can grant the power for the license. These are much bigger ones. It's not that, I don't think, I mean, obviously you'd have to get a permit to do a geothermal, like a small geothermal for your house, but it's not like the federal government owns your heat that you get out of your little geothermal. These are much bigger projects we're talking about. This is for reasons of both environmental protection and reservoir management. It's now becoming common to require re-injection rather than disposal at the surface. That makes sense. It says re-injection too is controlled. In Italy, for example, it's not permitted to re-inject into any aquifer other than the source. And in some places, there's just no legal definition at all. For example, the UK, it says that since the mining law is so complicated, different type of mineral resources being subject, there's no easy way to precedent to apply these very complicated laws to geothermal resources. But I think we'll see that changing shortly. Okay. That's about all I've got right now. This last little bit in the chapter is I think optimistic. It says estimates that geothermal could supply about 10% of electricity demand. It's not, nothing. It's not small. It's not insignificant, and it's. If we went back and looked at the slide from that 100% renewables slide that I put up a couple weeks ago, it'd be interesting to see how much of that, what Montana would look like, and then up to 3.5% by 2050. So that's 10 times. So from now to 2050, the industry is expected to grow by 10 times. So pretty impressive. Okay. One thing they didn't really talk really much about were home building and actually building homes closer to or in the ground. A lot of times you just look around at conventional home building, and a lot of them just look like big radiators. If you know what a radiator fin is, remember the old Stegosaurus with the bones sticking out of his back and sort of radiating heat away? Unfortunately, that's how we typically build our house. They're boxes, obviously. They're not thin spikes, but it's pretty good for heat exchange. But if you want to keep something hot, that's the exact opposite of what you want. So I'm not sure if you've seen the Buckminster Fuller domes or not, but that's an example where you've sort of minimized the amount of surface area. They're relatively low, close to the ground. The solarium up there in Browning is just unbelievable. Just a little bit of sun heats that thing up like nobody's business. They've got a giant concrete slab built into it with some water circulation going on in there, and it's just fantastic. Off-grid, free heat. It can be blowing like crazy and very cold outside, but the fact that it lets all that sunlight in, stores in that big thermal mass is pretty impressive. And when we get into integration next week, I think what we're going to find is that all of these renewable energies that we've talked about will ultimately become quite integrated. All right, I'm just going to pause the recording there.